means of this going through all the questions is to try to figure out what kind of things may have gone wrong in terms of weird question or other stuff that didn't supposed to behave as it was. I'm quite sure that there are a few, because I encountered a couple during the test itself. So what I'd like to do is simply go through the separate questions. Not all of them, because we will be able to see how many of you had the question correct. If the percentage is really high, then I suggest we do not bother with actually checking the questions. If it's really low, or the answer that is chosen the most was not the one that was correct, then perhaps it's a good thing to have a look at it. And I'm quite sure there will be typos or weird questions or wrong answers from my side in it as well, so it pays to pay attention so that I can make sure that we can correct all this. So here we see our first question there. Let's see if I can further increase this in size a bit. Okay, so this one is 70% correct, which is not too bad, I guess. Guess the correlation. This is the first one where I have to double check the answers. First of all, I think the correct answer was 0.67, and I do not know what happens if you type either a decimal comma and then 67. Not sure what happens then. It may depend also on what kind of language you have on your machine. Yeah?
If you miss the component to the comma?
Yeah, or another answer might be 6-7, because that's the only thing that you have to type in guess the correlation. So all these kind of questions I will have to, I'm not sure what I have to do, but in any case I have to check somehow, making sure that all these answers are correct, if they indeed are. The other thing is, of course, is how wide is the interval that you should reach here, and I stuck to 0.2, so minus 0.2 this or plus 0.2 that, which seems like a reasonable number to me, which is a bit wider than guess the correlation would allow. Yes? Oh, 0.27 and at the end 27? That would be in any case too low. So that would be wrong. Other questions about this one? If not, let's continue. 70% correct, and the one that was most chosen. So that looks fine. 91% correct, and also the one that was most chosen. This one too. Let's see, also the one that was most chosen, this one too. This is where I found out that I'm colorblind. This is sort of looked greenish to me, but apparently to many of you it looked blue. That one. Other than that, most of them have it correct. So this is just fine, this is also okay. 68%. That'll work. Here it's close. Which of the following statements is most likely to be an H0, so a baseline hypothesis about the world. The main rule here is you need to have some kind of equality in there, and this is the only one that has an equality. 5% of the students will graduate cum laude, so we have an actual 5% to work with. And the other one that was chosen, girls are more likely to graduate cum laude than boys. This is an inequality. So not useful as a baseline hypothesis, not useful as a H0. Let's see, also okay, this one is tight again. I'm predicting my target variable y with just a single dummy variable x. What does my prediction model look like? Well, your prediction model then is just a little bit better than just predicting the mean. If you would have no predictor in your model, you would just guess the mean for all cases. If you have one predictor in there that has two categories, let's say male or female, you get two numbers as a prediction, still not very good. One number, the average for males, and the other number, the average for a female. So that's exactly two numbers there, one prediction for both categories of x. And one prediction, just the coefficient of x. That's certainly not true. If you're aiming for the coefficients, then for sure also the constant term is in there, and these two together will give you the predictions, one for each of the two categories that you have. Let's see, this one is also sort of okay. This one too. Right, this is also fine. Okay, this one's sort of close too. Here I'll have a look if I really believe that it is super important to actually know this. Here you see that in the table, the number of observations is 74 everywhere, except for one case. So you could think two things here. The first one would be the one that's actually correct. There could be 74 cases in there or more. And the more could arise from the fact that there are quite a few empty cases in that data. That could work. Or if you have cases where, for instance, each and every variable has a single missing. So there are 74 cases in total for every variable, but there might be 120 as long as the missings are nicely distributed across these different variables. Okay. So it's sort of a tough question. So I'll think about the necessarily exactly 74 as well. We'll see how that goes. The alpha question was easy. This one we already briefly talked about with a couple of people over here. So the question is, you see the definition here of Kramer's V, the effect size in a chi-squared analysis. Why do we have that k minus 1 in the denominator of that fraction? And there is a sort of a typo in the answer here, because this one is correct, but not completely, because the chi-squared value is necessarily larger if the table is larger. This is, in a way, what I meant to say here. If you have a really big table and you have to compare the expected numbers, the expected frequencies, that is, with the actual frequencies, then you're likely to get a chi-squared value that is way larger, simply because there are so many different cells that you have to compare. But then still, the necessarily larger is not correct, because if, for some reason, I have a 10 by 10 table, so I have to check 100 of these cells, and they happen to be that they all fit the expected frequency exactly, then even with my big table, I would have a chi-squared value of 0. Whereas you, with a relatively small table, as long as your expected frequencies are not exactly on the mark, would have a higher chi-squared. So this is, strictly speaking, not correct. I should have put something else there besides the necessarily. So I'll do something with it. I'll have a look at what the other people had here. I think I'll simply disregard this question, simply also because all the other questions, all the other answers are not correct as well, in obvious ways. For instance, because the number of variables should be accounted for can be right. The number of variables is 2 in a crosstab, so that doesn't help. So that one I'll disregard. Somehow, I already checked the Canvas forums. Seems to be a wild debate about why can't I just delete a question from the list and then have all the grading automatically updated. So apparently this is not possible. So I don't know what I'm going to do here, but somehow I'll arrange that. This one was okay again. This one's even more okay. This one too. 71%, also not bad. 78. 15.9. Well, actually not that bad, actually. And here we do get into another issue. Two variables x and y have a correlation of close to 0. One thing that I didn't focus on here is if one of the two variables is a constant, or close to a constant, then you have either a vertical line or a horizontal line. Then, well, if it's close to a constant, you could have a correlation that's actually close to 0, but in a way it's a bit weird. As long as you have, let's say, normal x and y that really vary, instead of x and y, one of which do not vary, then the right answer should be the scatter plot of y against x cannot look like a straight line, because if it would, then the correlation would not be 0. So again, I'll have a look at these answers here to try and see how wrong I consider most of these answers to be, and we'll update the grading accordingly. one's okay. That one's okay. That one's okay too. That one worked. Okay. So as far as I'm concerned, that's it. The rest of the variables seem to work because the question that was chosen most often was exactly the right answer. Yes.
Question 10.
Question?
10.
Where do I see the number? Your question 10 need not be mine, so that give me some text from the question, then I can find it.
Over there. Rain.
Sorry? Rain? This one? Okay, you estimate the number of millimeters of rain in a given day based on the number of millimeters of rain the day before. You get an R squared of 0.9. Which of the following is true? Okay, it's a decent model for prediction purposes, but you have not learned much. Which other one is correct?
Yeah, so I thought regression is totally inappropriate because you're only measuring yesterday. So, come on.
No. What is inappropriate about it?
Yeah. This is totally inappropriate to do. Because
Why?
you did yesterday. Come on.
Give me an argument besides come on.
Like, I think regression is inappropriate because you only have one day.
So, I have an R squared of 0.9. If I want to predict tomorrow's weather, if I'm a weatherman, I'm doing a good job here. What's the point?
Yeah, I think because you're only losing one day, I cannot multiple days. Because from one day you cannot see better.
Now, the example is not that I'm using a statistical model here on one data point, right? I may have 1,000 days, and for each and every one of those 1,000 days, I have the number of millimeters of rain of that day before. Okay?
Okay.
So it's not that I looked at yesterday and I predict for the rest of the year that it's going to be like yesterday.
I have actually a completely different argument about the same statement.
Yeah?
Because I thought that regression analysis was one interval y and that many predictor variables x. And here's only like one variable x and not like with the example from age, gender, happiness, that will influence y.
Yeah, but that's simply a wrong answer. There is no need for regression to have more than a single predictor. And in fact, the last lecture is completely about you have one single predictor. So it's simply wrong.
I would say this is not a good model because this is kind of the first model we want to make, and it works. But if someone would say this is my model, we would laugh at them. It's not it's the simplest serious model. So it's I would add temperature, other variables. It's not a good model.
Depends what you want to. So the argument is it's not good because we can have better ones. But you know, the R squared is 0.9. So if the A is just prediction, it's fine. Oh, there I don't see strong arguments. Other questions about test questions here? Okay. Let's see. Okay. A couple of last issues about the test. This is the part where the laptops can go. The last couple laptopers, please close stuff up. One question over there, yes? Yeah, I'll make sure to put the quiz back online in such a way that you can actually see the right answer as well as soon as I found the right button to click in. A couple of things that I noticed. First, the submit button at the end. It looks like for each and every question, all the way before 40, you can click next for the next question. And if you have completed your question 40, then there was a button that sort of looked like the next button, but then said submit. So if you didn't pay close attention, you could have accidentally clicked submit and then would have submitted immediately, I think. I'm not sure that I can do anything about it. I think I cannot, but at least it's something to be aware of for the next time. That as soon as you reach the last question, if you accidentally click that submit button, then you have submitted and it's done. Okay, so that's something that I can check if I can do something about it, but I doubt it. Something else that I saw that went wrong in a couple of cases is that if you use your browser back buttons, then maybe it works for some of you, but for sure it didn't work for others because you got stuck in a page not found or something like that. If you then would go back to the original page, log in again, then you would be able to resume the quiz. So it wasn't detrimental, but still it's annoying. So for next time, try to stay away from those guys with back buttons. Third one I already mentioned, decimal points versus decimal commas and stuff. I have to check what happened here and if I can do something about it. In the end, what I will do is what's called monkey grading, so I will subtract a little bit or take into account the fact that if you just randomly click your answer, then roughly you have about 1/4 of all the questions correct. I'll have to check how many questions I'm left with after the 40 that we started with, and perhaps we lose a couple. And then you'll find out soon enough what the grading exactly is. But you, let's say, loosely speaking, if you would have 40 questions, all multiple choice, and we had all of them complete still, then I would say something like, well, 25% of that, that's 10. So basically 10 you have if you just guess. I'll go a little bit below that, so let's say 8. For the first 8 questions that you have correct, don't count. So then what you can get is at most 32 correct. So you look at what you have, let's say you have 28 correct or so. Subtract 8, that's 20, and you can score a 32 at most, so you have a, 20 out of 32, what's that? Sort of like a 6, I guess. So something like that will happen, but all that after that I've completed the whole regrading process. Any other test-related questions? Also about how this went? Anything that didn't go as planned?
You cannot go from, for instance, question 40 back to 25, then you have to press back 15 times.
You can click the question on the right.
Oh, okay.
Other issues? If not, okay, then I'll continue with today's stuff. And today is sort of a separate module. One that you can follow even if you scored very poorly at the test and didn't make much of the stuff that I've been talking about this far. It's all about the determination of sample sizes. So this is where we were. Grayed out once again the stuff that we all did, been there and done that. And now something totally different that we put in between here, that is sample size determination. Also gives you sort of a breather from the rest and some extra time to keep up. As soon as this is done, we'll continue with regression analysis, and we had this far regression with one predictor variable, and we'll go on to more than just a single predictor variable. But first, a little bit about sample size determination. There's not a separate chapter in the book about this, but the stuff that we will cover is, in fact, considered in a couple of separate chapters. If you look at the reading guide online, then you'll exactly see in which chapters that is. And there are only a couple of commands to consider, so we're actually should be good to go. Okay, so let's see where we are in the whole setup. This is your standard how do we deal with data setup. We import a data file, we check our data, we determine what we want to do, and then we do something like factor analysis. We didn't cover that yet. That's measurement, then we check our assumptions, then we run our analysis, and then we check again. Okay, this whole process is assuming that you have your data already. And the stuff that I'd like to talk about is actually a bit before that. This is your typical do file. When you actually get the data from me, and the most important part is as soon as you find out in your data that you don't find what you had hoped, then the last thing that you want to have is that at that point you find out that your sample size was not large enough and that it was not likely that you would find anything to begin with. And that's actually something that you need to do way before the actual data collection. So when, let's say, all this starts to become real and you do your own experiments or surveys or what have you, then you need to think up front how large the sample size should be. And you can, if you do this wrong, then you might be totally screwed. So let's see. Normally, you collect your own data. A typical bachelor end project or a typical master thesis is of the kind you think of something to figure out, and part of that is that you create an experiment and run an actual experiment, and then you think beforehand how large your sample should be. What's that? So the sampling is, before that, I'm doing the sampling in the hope that it will give you sort of a distraction from the standard stuff that we're doing, and I hope that I do not mess up your mind too much because it's now something completely different. So just to help you out a little bit, this is what I'm in the end aiming for. So these are the conclusions that I'd like to draw. Here's a 2 by 2 table, and the main thing to remember, if you only remember one thing, is that if your sample size is too small, then do not even start the whole research. That's actually what the main message in a single line would be. So let's consider the following cases. First, normally what you're aiming for is to find a statistically significant effect or difference. You have 2 conditions or 3 conditions or what have you, and what you think is, well, this is the baseline, and here I'm doing something, and I'm guessing that what I'm doing here works in the sense that what happens now is different from what I had before. So usually you're hoping to find a statistically significant result. Now let's see, let's compare, well, small and large samples. The question will be in the end how small is small and how large is large, but for small, think actually too small, typically let's say 30 or so, and for large, think a couple thousand, if you want to get a bit of a feel for what these numbers usually are. Well, suppose that you're here. You find a statistically significant effect, and you have a small or actually too small sample size. Well, in a way, this is just luck. We have a really small sample size, and that means even if something is there in the population, the chances are really slim that you'll find it with your mini sample. Okay, but you did. Not really clear how that happened, but you did. So this is in a way a good thing, but not something that you can count on. It can happen, and then it's fine. But more likely, it won't happen at all. So if you do end up here, well, that's a stroke of luck. Now let's see what happens if we end there. We do not find a statistically significant result, which is a bit of a pity, and we have a really large sample size. So that would mean, well, it's good and bad. It's bad in the sense that we're aiming for something where we find a difference, and we don't find it. So this is sort of a bummer, but because we thought if you do this, then something happens, but well, it doesn't. On the other side, you could argue this is really good, because now we are quite sure, actually, that there's nothing there. Because if there would have been something there, we would have found it with our huge sample, and now we know for sure that it's not there. So, let's say, statistically speaking, this is actually perfect. The only thing is that, we had hoped to find something, and we didn't. Okay, let's see. Then we have, we find something significant, and we had a large sample. Okay, at that part you need to think. The rule that you should remember here is that with a really, really large sample, any kind of difference, however minute, will become statistically significant. So you find something here, it is statistically significant, but you have a really large sample, and you have to check if it is substantially interesting. In a sample of 40,000, let's say, Dutch people, you find a difference of 51%, whatever it is, versus 51.1, and it might be statistically significant. Great, I find something, but the difference in itself, depending on what it is that you measure, is in all likelihood totally uninteresting. So if your sample is really large, then still you have to check, okay, the effect size that I have, is it something to be of interest or not? And it could very well be that even with a small effect size, it's still interesting. Life or death is at stake, okay? Might be interesting enough, these couple percentage points, but otherwise, yeah, you have to think carefully about how interesting it really is. And finally, the last place where you want to be, you find nothing there, and you have a small sample size. Okay, there you really do not want to be. And you run your bachelor end project, and you see coming up front that you want to run interviews, and they take quite some time, and you estimate, okay, I can do 25 of these. Now, 25 for almost all practical purposes is really too low. So in all likelihood, yeah, even if there's an effect there, you won't be able to find it. So 25 interviews is fine for qualitative purposes, but to do something quantitative on, in all likelihood, this is not good enough. And that would simply mean don't do it at all. Don't start the interviews. Okay? Don't wait until you have collected 25 over the course of weeks, and then find out, oh yeah, it's not very likely that they find something anyhow. You don't want to be there. You have to arrange something else. So for these 4 boxes, this is typically what you need to do. First, well, if you end up there, you have to start over, or keep collecting more and more and more until you have a sample that is large enough. This is, well, you found something under the circumstances that were difficult with a small sample, and in all likelihood, you are just lucky. Here, you find a strong indication that nothing's actually there, which is statistically okay, but usually substantially not very interesting, or not what you were aiming for. And here you found something, but yeah, here the sample size is so large that it's actually really likely that you find something, however small it is. So then you have to check if it's substantially interesting. Okay, so these are let's say, the places where you can end up in the end, and you now know what to do, which leaves, of course, that we have to calculate somehow what the appropriate sample sizes would be. And, well, 2 rules to remember. First, you do it before you collect your data, because otherwise it might be too late. And typically, I would say, intuition is such that they are normally larger than what you think. Depends a little bit on what you think, of course, but in general, students tend to believe that with a relatively small number of cases, you can still do something. And if that number is still a bit lower, then we do a little bit less, but that's just nonsense. We'll see. Sample sizes. 2 commands in Stata. One is called power 2 means, and the other is called power 2 proportions. The one is for a t-test, and the other is for a probability test. And something else that we already covered before are these rules of thumb that we saw, the 1 over square root n rule, that one we had. For estimating a proportion, we know what the confidence interval in the end looks like. 1 over square root n to the left, and 1 over square root n to the right. And that would be if you want a confidence interval around some proportion to run from that number that you find minus 1 percentage point to that same number plus 1 percentage point, that would mean an n of at least 10,000. So we're estimating a proportion of something. You want to be really precise, plus or minus 1%. You want to be able to say, fine, then you need 10,000. Otherwise, that's not going to work. And here you see a couple of other examples, just to give you a feeling for how good or bad it becomes. For n is 25, you're sort of restricted to saying something like plus or minus 20 percentage points. If that's good enough, great. If you need something more precise, too bad, then you need a larger n. And you'll also see typically here that if you want to be really close, then that number goes up pretty fast. So here you see an extra percentage point here, plus or minus 2 versus plus or minus 1, will cost you an extra 7,500 subjects, which is quite a lot, and usually very expensive or simply not easy to do. Then do realize 1 over square root n, that's an approximation actually. If you're talking with somebody else, how large should our sample size be here? Let's just get a feeling for what that number might be. then that 1 over square root n rule is good enough. However, the exact answers are slightly different every once in a while. For instance, here I see the actual answer from Stata. Stata does it the right way. So here you see 100 out of 400. That would give a confidence interval from 20 to 30, which is about right in the sense that the 1 over square root n rule is pretty close here. 1 over 400, 1 over the square root of 400, that's 1 over 20, that is 5 percentage points, which is right. 25 minus 5 is 20, and 25 plus 5 is 30. Same thing here, also 400, but now I look at proportions really close to 0.025. Well, there, the rule of thumb doesn't work anymore. We should have a look at Stata here and see that Stata says that it's running from 1.2% to 4.5% instead of the 1 over square root n rule, which would have gone below 0 actually in this case. So if you really want to know it, make sure that you check in Stata. Yeah.
Sorry, what was the rule of thumb?
1 over square root n is the 95 rule that gives you the 95% confidence interval. So here we have a proportion of 0.25. 100, let's say yeses out of 400 cases, 0.25. I want to make an estimate of the 95% confidence interval here. And I want to say something like 25% minus something and 25% plus something. And that something is 1 over square root n big. N is 400 in this case. Square root of 400 is 20. So 1 over 20, that's 5%. So this is why I have 25% over there, minus 5, and plus 5. And I would be tempted to say the same thing here too, but here, minus 5, this is only 2.5% already. That would go below 0. Certainly doesn't work. And it also doesn't work the other side, actually, because plus 5% here would be 7.5%. And in fact, it's only 4.5%. So the 1 over square root n rule is a rule of thumb, a crude approximation, and nothing more. Another one that we had for correlation, again, you see numbers here where you might worry about how am I ever going to get samples that are this big. A correlation is significantly different from 0 when that correlation is larger than 2 over the square root n. If you rearrange that, you get this, and you see that if you want a correlation of, let's say, 0.05 to be statistically significant, then you need already 1,600 people, which is quite a lot. For 0.3, then 45 would do. For 0.2, you need 100, so that gives you a feel of how many you need. And that will, for the really larger samples, you'll be able to get even these significant, but you could wonder about if you're interested in a correlation this small, because in all likelihood it won't predict very well anyhow. Okay, so let's see. Let's suppose we're trying to test this assertion. We have two groups, students from here, from TUE, and we have students from somewhere else. And what our guess is that the IQ on average of the TUE students is 120, and the group of the other students is 115, slightly lower, of course. So now the question is, if we want to test this, and we would have gotten the data somehow, then we would be able to run a t-test. IQ is interval scaled, and nicely interval around 100 for the, let's say, the average person, and for academics, perhaps a bit more to the right. Excuse me, could you get rid of the phone up there? Great. We also know that standard deviation is 10, so we know a little bit about if this is the distribution of IQ, how wide that thing is. So if this would really be the case, we have two groups here, one of a mean of 150, one of a mean of 120. We have something like this, that's one group, and another group slightly to the right, and we have to sample from that group in some way, and then try to figure out if indeed we find a significant effect here using a t-test. Now that we can actually relatively easily do. There is a command for this, but I'd like to show how it works if you don't have the command. And the advantage of that is that that method always works. So let's see if we can get this to actually work. this data. Okay. Can I increase this? Bit. Okay, well, that should work. So let's see, what I'm trying to accomplish here is a general recipe of trying to find a decent sample size for any kind of analysis that you want to run. And the good thing about it is you do not need any statistics other than that you need to know what the command is that you want to use afterwards. And that we know, namely t-test. All these kinds of analyses are running in the same way. First, we're trying to create, let's say, the world as we think it is in Stata. Then we are going to sample from that world and then see how it goes. That's basically what I'm trying to accomplish here. That starts from this part over here. I clear everything. Set more off will ensure that Stata will keep on producing output. I create here a population with 10,000 cases. I could have used many more, but then the analysis will run for quite a long time. And I create another variable here. Okay, so at this point I have simply 10,000 cases in my data with nothing in there. Here I create two variables, one with IQ with a mean of 120 and a standard deviation of 10, and one with a mean of 115 and also a standard deviation of 10. So the first ones are supposed to represent the TUE students, and the second ones are supposed to represent the other students. So now I have two variables in my data. One is called IQ TUE, and one is called IQ others. And of each of them I have 10,000 cases. Now let's see what happens if I run this up to here, just to check if this is actually working. And indeed, well, first of all, it only stops there, which is nice. I have 10,000 observations here. This one has a mean of 119.9, and this one has a mean of 115. So that seems to work, and for both the standard deviation is indeed about 10. Okay, so I've created the population here in such a way that this is actually what I think the world looks like. You have TUE students on the one hand, they score on average a 120. And you have other students on the other hand, and they score on average 115. Okay, next part. What I'll do here is, well, I basically give it a try. I have 10,000 in the population, and what I do is, in this example, I put my sample size at 50. So I'm sampling 50 TUE students and 50 other students, and I compare the two with a t-test, just to see if that works. The only issue here is, of course, if I do this only once, then my results are totally dependent on that single one draw that I tried here. So what I'm going to do is I will draw 50 students from TUE, 50 from the other ones, and compare, and keep track of whether or not I find a significant difference. If I find a significant difference, I add it to, yes, I found it. If I do not find a significant difference, I add it to, no, I didn't find it. And that process I repeat many times, and where many in this case is, just to make sure that we can conclude this in finite time, is 1,000. So what I do is 50 students from the population from the one group, 50 from the other. I run a t-test, and that process I do 1,000 times, just to see how many times I would actually find a difference, given that it's there in my data. Well, you can have a look here at how I do it. You do not need to know this yourself, but somebody asked before if you have for loops and so on. Excuse me, could you stop talking? So you have for loops here in Stata. It's called for values, and as soon as you see it, you can, I guess, see the logic of this. I'm keeping track of how often I find a significant difference and how often I do not find it. And then I give you a tab in the end. How often do I reject my H0? Now what I want to find here is that I reject this quite often, because I have a population here where there is a real difference between the groups, so I want to be able to conclude that there is one. So let's see what happens if I go from 50. Let's see. Sampling all the time again. 50 actually would mean that my true sample size would be 100. 50 from one group, 50 from the other. Let's see if that would be enough. Almost there. Okay, H0 is rejected. Well, how often? 68% of the time. So this would mean if I'm, after this, my population really looks like 120 versus 150, and I go for a sample of 100, two groups of 50, then I will only conclude that there is a difference in 70% of the cases. This is rather tight, I would say, given that we know here that there is a difference. So you would like to have this number at 100%, but that will never be reached because, you know, it's a sample. It's not the whole population, so you cannot have certainty. But what we want to have typically here is, let's say, a percentage of 90%. Just like the alpha is typically standard 5%, typically what we settle for here is we want to be 90% certain that we find an effect if it's there. So in this case, we know it's there. We want to have 90% over here. So let's try something that is a bit higher. If I remember the answer correctly, it was 85. So that would actually be 85 times 2, so 170. And what we're hoping to achieve now is that at least in 90% of the cases, we find that there is a difference. And let's see if that actually works. Yeah, slightly more. In all likelihood, there is some noise in here. I could increase that 1,000 samples that I tried to something larger if I had time, or I could increase the population even more just to make sure that you do not resample the same cases every once in a while. So that would make it even better. But still, this is suggesting for 170, 85 from one group, 85 from the other, I'm sort of fine. Yes?
Could you run it once more with 120 or something to see
Sure.
if that would be even much better?
So you can play around with this. If, for instance, let's say collecting data would be super cheap, so you know, 120 times 2 would be 240. If that would be no problem at all, then yeah, we might actually want to do it just to make super sure that we will find something if it's really there. And in this case, it's ending up to 96. So better. You could of course argue about 91 versus 96 if it's worth it. Depends a little bit on what it costs in terms of time and money, but the bigger you get there, the higher, or the closer to 100% you're going to reach. Yes?
I had a question about the 90%. Is it
Yeah.
just a rule of thumb? Like, it's not like alpha where we have always 95%.
No, yeah. It's tempting to think that just like alpha equals 5%, this number here is then likely to be 1 minus that. But they are totally unrelated. You can choose here whatever you like. It's called the power of the test. How likely is it that you will find something given that it's there? Typically what we normally use, for instance in our own labs, is 90% to do the calculation beforehand. If we have something where we are, you know, just a pilot study of something, we sometimes settle for 80%. But any lower than that would simply be, yeah, usually a waste of resources. Other questions about trying to figure out what my sample size is supposed to be? Theory students have an IQ of 120, others have 115. If that would be really the case, what would my sample size be? We went through Stata and did some simulations there. And then we found out, well, sort of 85 was about enough. 85 of each, so 170 in total. That would work. That would work because then we would conclude in 90% of the cases, if we run a t-test on the data that we get on these 170, then indeed we will conclude correctly that there is a difference between these two groups. And I want to conclude that there is a difference because this is exactly how I created the world in the beginning. So, what would that mean in general about these kind of things? Simulations for sample sizes are always of the same kind. First, you create a world in Stata or any kind of other program, doesn't matter where, that resembles the kind of thing that you want to be able to distinguish. We looked at 120 versus 115, but it could be anything that you would want to compare. That you create in Stata. Then what you do is you start from a sample size that you hope is reasonable, let's say 100 or so, and you check. If the world is like this, I created the world with the difference that I'm interested in finding. If I sample 100 from that world, would I then indeed conclude that there is a difference? I cannot do that once, I have to do that a lot. Here, I said 1,000 times or so, or if you have time, take 10,000, will certainly be better. Then you want to conclude as often as possible, typically 90% of the cases, that indeed you find a difference in that world that you just created. And you play around with the actual sample size until you reach that indeed in 90% or sometimes 80% of the cases, as mentioned in the book actually, you will indeed find a difference. Depending on how complicated the thing that you are trying to test is, these simulations will become more and more complicated. And luckily there are a couple of commands for this as well, so we do not need to do this all the time, but I think you'll find out, at least over the years, that as soon as you run your own experiment, very fast you run into trouble in the sense that the sample size calculations are not so easy anymore, or outside the realms of the stuff that we can typically do in Stata or in other software for that matter. Okay, the good thing about this is we're trying to figure out sample size, and the only thing that we need to know in principle here is how to run a simulation in Stata, which, not necessarily easy perhaps, but we don't need statistics for it at least. And the other thing is, what I need to be able to do is run whatever command that I need to try to find that difference. So in that example, it was a t-test. If I would need something else, a regression or a correlation or a chi-square test, as long as I know how to run that command in Stata, then I'm just fine, and I can actually do this. So we need not resolve to any kind of statistician who delivers us a formula of any kind. Okay, what we need to know up front for all these kinds of calculations. First, what you need to know how large the difference is that you want to be able to find. And obviously, if there is a big difference that you want to be able to detect, your sample size can be smaller. If there is something really small that you want to be able to find, you need a larger sample size. Then, typically, how large you allow the probability that you mistakenly reject the null hypothesis, that is our standard alpha, or 5% usually. We do not mess with that. And then the third one, that is one that is new, the power of the test. How likely do you want to be that you indeed conclude that there is a difference, given that it actually exists? Well, yeah, it would be nice, 100%, but that won't work, because we have a sample and not the population, and typically we stick to 90% there. The power of the test should be 90%. And actually also what matters here is whether or not you do the test one or two-sided, but for now we can forget about that for a minute. So these are three things you need to know up front before you do any sample size calculation. Okay, and I cannot emphasize that enough, you do it before you actually collect the data. If you find out afterwards your sample is too small, all the work was typically for nothing. Let's see, yeah. The example was using a t-test, and let's say the recipe was general enough that you, in principle, can do this not only for a t-test, but for any kind of test. But it does show that you need to rerun this whole thing depending on what kind of test that you do. So now we have a sort of a way to do it for a t-test. But if you have something else, then you have to rerun the whole analysis, rewrite the whole thing, now not for t-test or something else, and then you'll figure it out as well. But for instance, if you're interested in the difference between two proportions, the difference between two means, the confidence interval for a score, the relation between x and y, the relation between several x's and one y, all these work in the same way, but all these require, let's say, a new do file with a new simulation run, trying to figure out what the actual sample size is. So, yeah, in a way, the strong point of this, that you can do it all yourself, is also the disadvantage. You have to do it yourself for all these, separately for all these separate things, because it won't work automatically. Okay, this part was an example that I'll skip because of the time. We had the t-test example. Here I had a proportion example where we have two groups in this example, men and women, where, let's see, the question was just a fake question, who's more likely to own an Android phone? And we have yes or no. For men, we have 30% owns an Android phone. For women, we have 40%. So this is a comparison of two proportions. 0.3 in the one group versus 0.4 in the other. What is the typical sample size that I need? Well, I can show data here, but I won't give it the time. I have a do file that does exactly this. You can try to figure out what happens here. And here you would see, if you would go through that same exercise, that we need quite a few, actually about 950. So 475 males and 475 females. So in this case, it's actually worse than for the t-test exam. Let's see how bad it actually is. If we have a comparison of 30% versus 40%, we get at, let's say, about 1,000. That 950 that I just mentioned is that need about 1,000. Here we have 0.3 on the horizontal axis, and you see here for comparisons with 0.3, here's at 0.4, that's over there, that's 1,000. And here you see it grows fast the closer you get to 0.3. If you have a really big difference here, 0.3 versus 0.9, okay, that is a massive difference, then you then you still need 60 to make sure that you can actually find that with a reasonable probability. 0.3 versus 0.35, you already need 3,800. So let's say 4,000. It goes up pretty fast. Anything that is closer, I want to be able to find a difference between 0.30 and 0.31. Okay, start paying, because this is, in the tens of thousands, if you want to be able to find a difference of that kind. That brings me to an example that we had in the questionnaire, way in the beginning. The example was as follows. If you want to know the percentage of people in the Netherlands who support the recent foreign something, doesn't matter what, and the Netherlands has 12 million persons old enough to have an opinion, and you do your sample size calculations, for instance, through Stata, and you find, well, I need a sample of 2,000. Now you want to do the same, but you want to do it in France. France has 3 times as many voters, so how large should your sample size be? And this one actually was, I think, even literally in the sample. And the rule of thumb that you need to remember here is that even though you might be tempted to think, well, this is 3 times bigger and 2,000 there, then it must be about 6,000 because somehow population size should be in there. This is actually not the case. As long as your population is in size quite a lot larger than your sample is going to be, as we have here, 2,000 versus 12 million, then you can simply disregard the population size. So even if we want to be representative for the world, let's say, then still the sample size wouldn't be any bigger. It would be, of course, a massive effort to randomly draw 2,000 people from the world population, so that would be complicated. But in principle, if you need 2,000 for the Netherlands, then you need 2,000 for larger groups as well, which sort of goes against our intuition and also against yours, because, oh yeah, I had one, I think, I'm not sure if I used this one. I may have used another one. Yeah, slightly different answers. So here the number was, let's see, 400 respondents is okay for the Netherlands, and now for France, which is 3 times as big, and then you should say also about 400. So in this case, the correct answer would be B, which was answered by 32% of the people in this data. I think in your data it was roughly the same. So this really goes against intuition. You tend to think must be more, but that's really not the case. So do I have that here? Yeah, this one's correct. And this is totally weird and also really misunderstood. If you have followed, for instance, who was that again? Robert Jensen, who was in the States trying to figure out where all the polls were leading for the American election. He also literally said to some statistician, yeah, but all these polls must be nonsense because they poll 1,000 people and that cannot be representative for a really large group. Okay, that's total nonsense. Of course, Robert Jensen is perhaps not the key authority on these kind of issues, and he was showing it because this is typically wrong. 1,000 can be very representative for a larger group, but we have to get a bit of a feeling for why that is, and it's not so easy. It still goes against my intuition in a way. Okay, let's see how that works. We're sampling and we get measurements, and what we're aiming for is the mean of that sample and what the distribution of that mean in the end is going to be, as you've seen before. Well, the mean of the sample, that's not so complicated. We add all the separate measurements up and we divide them through how many we have. Okay, that's the mean. Now, an estimate for the variance in the population. Well, how does that work? Looks like this. In this formula, what you see is, well, a couple things. This one, the S squared over there, this is the variance in the sample. Makes sense. The only thing we can calculate to estimate the variance in the population is the variance in the sample, because that's the only thing that we have. So that S squared is in there is not a weird thing. And that the large n and small n are in there is also not so strange. The large n is the population size, and the small n is the sample size. So that it has something to do with that. We can live with that at least. Now let's see. This and that together we can use to come up with a confidence interval for that mean that we're after. And the confidence interval looks like this, the thing at the bottom. Now, again, you see that 1.96 that we have seen before in normal distribution. Not that matters much. The point here is the left border and the right border, the width of that interval depends on this thing over here. The square root of that thing, but in any case, this part determines how far to the left and how far to the right the confidence interval is. Okay, now let's look here. If large n is really much bigger than small n, then n minus n over n is just 1 for all practical purposes. And large n simply disappears from the whole equation, and also disappears over there, of course. Suggesting that how precise your estimates are basically has nothing to do with how large your population is, as long as large n is way bigger than small. So if your sample size is, let's say, half of your population size, okay, then matters start to become different. But if you have 2,000 versus 12 million, or 60 versus 6,000, then for all practical purposes, population size doesn't matter at all. Okay, that's hopefully helping a little bit in terms of your intuition here, and the easy thing to remember is, okay, population size doesn't matter as long as it's big enough. Any questions about that? Okay, then, luckily, we do not have to simulate for many of these different kinds of analyses because there is software that will do it. It used to be the case that, that there was dedicated software just for this. I think still in SPSS, for instance, there is nothing that says something about sample size. In fact, for a long time, this program here is freeware actually, G-star power, and it only calculates sample sizes for different kinds of designs. It was the only thing that was there. And there are here and there online sample size pages, which are a bit risky because you never know what they implemented, so you get an answer, but you have no clue if it's true. And since I think version 12 or so from Stata, we can also do this in Stata. And one other one that I want to mention, just because it's relatively easy, is the program is called PS for power and sample size. Also does nothing else than power and sample size calculations, also freeware. For Windows, by the way, that G-star power is also for a Mac. And that stuff will also work quite well for the simpler designs. Okay, we'll obviously go with Stata because we all have that. If you have, by accident, a very old version of Stata, version 12, then you should upgrade because the commands change a little between version 12 and 13. So there might be a couple of people around who still have that. Make sure that you upgrade to, well, 13 at least, or just use the 14 that we have online. Yeah, then again, you see that if you want, you can go through Stata's graphical user interface, where under statistics there is a power and sample size, and then you get here all the different kinds of over there a way to try and find the one that you actually need. So if you know that what I want to do is something that's related to, well, there's needs, if you click there, then here you only are left with the ones that are about means. It's actually way easier to simply remember the command as usual, and that is what we will do. All the data examples that we will go through here are about comparing two groups, and let's see. First, let's try to recreate what we did before in our simulations. This is the command that we'll use. Power two means. What are two means? 115 and 120. Because we're comparing two means here, basically we're assuming that we are comparing two interval scale variables. For that we need to say something about how wide the distribution is. The standard deviation was 10 in our case, because I know that this is the standard deviation IQ. And the power that I want is 0.9. I think if I leave this out, Stata will assume by definition a power of 0.8, which I find a bit on the low side. So you have to add power equal to 0.9. And then you get this estimated sample size for a two-sample means test. A t-test assuming that both of these standard deviations are equal in both of the groups. If you want something else, different standard deviations in both groups, that could work too. Then you type there SD1 10 and SD2 20, if that's what you want. And then you get back, well, an alpha, 0.05, you didn't mention that, but this is what Stata is assuming if you don't mention it. Power of 0.9, well, we ask for that. Delta, that's the difference between the two means. The two means itself, the standard deviation, so basically all this is what you inputted already, besides the alpha value. And the estimated sample size, 172 or 86 per group. So that's in one go the actual answer that you need here without going through all kinds of complicated simulations here. Typically what you are trying to figure out if you do this in practice is, how large should my sample size be and how bad would it be if I do a bit less, or how much would I win if I do a bit more. And command allows this by, for instance, asking for this, give me power 0.6, 7, 8, and 9, so that I can compare how much better it gets as my sample size increases. And here you see, where we have that, total n, 82, all the way up to 172. And here, these are the subpoints for the groups, for increasing power value. So the more certain I want to be, the larger my sample size is supposed to be. If, for some reason, sampling is very cheap, and I might want to go above 0.9, even to 0.95 or 99, who knows, then I can calculate also how high it should be, that sample size. If you're not even sure, for instance, about what that standard deviation here is, and also not so sure about the extent to which it matters. Oh, did I have that? Yeah. You can even ask that. So give me a list for different power values and for different standard deviations. So then, depending on what I find there, I can consider how reasonable it would be to, for instance, triple check here what these standard deviations are. Now, obviously, a table like this is not very intuitive, and if you add the command, the option graph behind it, you get these same numbers, but now in the graph. So here you see on the vertical axis what the sample size is supposed to be. For instance, if you know how much budget you have in terms of time and money, then you can already see, well, let's say the best that I can do is, for instance, 300. Then you know exactly what it is that you can accomplish and what it is that you cannot accomplish. And if you figure out that 300 is simply not enough to have a decent chance to find something, then just don't start it. Do something else. Come up with a different design or research something else, and that would be just fine. But don't start it and then in the end find that you get nothing, simply because the sample size is too small. Okay, now let's see if we understand what the what's called the comparative statics are. If the standard deviation rises, well then what? Let's see, standard deviation goes up from here to there. Right, so the orangey line is the largest standard deviation, and the bluish line is the smallest standard deviation. So we see that the bigger that standard deviation is, the larger the sample that we need, which makes sense. So we're comparing two normal distributions. If I have two normal distributions with a small standard deviation, so that's it, and another one there, that's easy to compare. So a sample size need not be that big. if I have two sample sizes, two standard deviations that are really large, that means I have humps that are really wide, they overlap to a large extent and makes it more complicated to find differences between the two. So the fact that these lines are higher for larger standard deviations is not so weird. And obviously, well, what happens if power rises here to the right, and we see also that these lines go up. Power is how certain you want to be, and you obviously find that if you want to be more certain, you need a larger sample. Also not so weird. Okay, let's try a couple of these differences to see which kinds of numbers matter here. This one. The difference that I looked at was 115 versus 120, and actually the only thing that matters here is the difference, not where they are. If I'm comparing two of these humps, if I take both of them and I move them somewhere else, I'm trying to find the difference between the two, it doesn't matter. Okay? So if you look at 100 versus 105, that's the same delta of 5, you'll get exactly the same result, and understandably so. If you are a bit more lenient, let's stick to an alpha of 10%. Don't, but if for some reason somebody would suggest this, then you'll see that the sample size goes down. Also for obvious reasons. But easiest is forget about this. We don't want an alpha of 10% at all. Who would want that? And every once in a while you could argue it's reasonable, but you open up yourself to the argument, you just added a larger alpha to make sure that your effects fall through. Now indeed you find effects that you wouldn't have found if your alpha would have been 0.05. So forget your argument about why it is reasonable and just stick to the 5%. Okay, one other one. Thus far we looked at a t-test where we just comparing group 1 and we measure the mean, and group 2 and we measure the mean. Let's see what happens if we have one of these other t-tests. And one of the other t-tests that we had was a t-test that was paired. So I have two measurements, let's say your IQ before I injected you with some weird concoction, and your IQ afterwards. Okay, so you are your own control in a way. I measured your IQ before and afterwards. And here you see part of the data was 114 before, and after the injection it was 121, and 103, 136. 99, 110. Now we see here, first, if I have a correlation here between these two measurements of 0, these measurements are not related at all. That is basically saying we do not have a paired test. That's basically saying we have two different groups and they are not related at all. So in that case, I get an n of 87, and my total sample size would be 87 times 2, because I have to measure 2 times for every person in the day. So that is the same as what I had before in the case where I didn't look at paired means. Now let's see what happens if my correlation goes up. Here I have correlation from 0 to 0.2 to 0.4 to 0.6 to 0.8. And you see here on the vertical axis what that does to your sample size. And you see clearly that sample size then goes down. Okay, so the higher the correlation between these measurements, the more I can, let's say, get rid of larger samples. Now let's see why that is. Here, that whole idea of these paired samples works because you are your own control. If I'm just trying to figure out, is that serum working, and I ask for, let's say, 100 persons, I measure their IQ, okay, go home. Now I ask another 100 in the lab, I inject all of them, and now I measure IQ. That would be a t-test that is not paired at all. I have here a group and I have there a group, that's it. Now I look at you yourself. You might have a really high IQ already, very likely, 145. And now if I inject you, you get, let's say 5 higher, 150. That 5 works for you, but you are already quite high. If I have measurements that are, where the correlation between this left column over there and that right column over there is high, then the fact that you are your own control is working very well. I'm taking into account that I'm doing something on you twice. So all the quirky stuff that is inside you is inside you there, and inside you there, and if I subtract the two, let's say all the mess inside you gets deleted. I get rid of all the noise. This is why within subject design is usually very useful. And the higher the correlation here is 0, and it doesn't help. But if it's 0.8 or so, then the sample size will go down dramatically. That really, really helps. There's a small caveat here. If you look at this in more detail and take into account something that we don't do now, that these things over there themselves are measurements and therefore not precise, then this benefit from the paired t-test gets way smaller than it appears now. So do realize that, you know, it sort of look like a total wonder here that we are decreasing our sample size from 87 all the way down to say 20%, which is dramatic. Well, in practical terms, it's not really that good as it appears here. But still, the paired samples is actually working well for us. And at least we should be able to see here that indeed for higher correlations you get smaller samples in general. Let's see, that's the comparison of the means. There's one other command left, and that is the comparison of the proportions. Same thing, now instead of two means, we type two proportions. The example that we had was 0.3 versus 0.4. Once again, we type power 0.9, otherwise Stata will assume that we mean 0.8. And we get here, well, let's see, our alpha of 0.05, our power of 0.9, the difference, delta of 0.1 here, and the two separate probabilities that we are comparing. And that leads to a sample size of here, 954. Yes?
What do you exactly mean with proportions?
This is the example where we measure the proportion of people that owns a Android smartphone, which I guessed here at 30%, way higher I think, but for one group, males, and for females it is 40%. So you can think of a question that I asked to a group where the question itself can be answered by yes or no. And then I look at the proportion of people that has answered yes.
So it's basically just another example.
Yes, this one is the same example, just as I had the IQ example. For the t-test, here we have the two proportions. And there we also have a command that will give me 950. And the 950, that's something that I didn't show, because given the time, I didn't want to show the other simulation. There was another question. Yeah.
But it's not related to paired t-test.
No. We're not t-testing here, we're comparing two proportions. Okay, we find 950. Expensive to be able to find the difference between 30% and 40%, apparently. Now, let's see. One thing that is missing here is that there is no standard deviation. So for the t-test, we needed that. We needed the two means and the two standard deviations. To say something about how wide the distribution is. Here we don't, and there is a reason for this. And that is, well, if I have something binomial, then the expected number of yeses is n times p, if p is the proportion. So if p is at 0.3, it is 1,000 times 0.3, or if we're flipping a coin, then we expect 1,000 times 0.5 or 500. And the standard deviation, so how wide the distribution is something like this, the square root of n times p times 1 minus p. Forget about what that exactly means, but it is completely defined by n and p. I need nothing else. So for binomial stuff, flipping a coin and so on, then the standard deviation is defined in terms of that p and that n itself. I need no other number. So if you there assume 0.3 for p, then I know what the standard deviation is going to be, even without you telling me anything. So here you have our example, the coin toss, 1,000 times 0.5 is 500, and the standard deviation, 1,000 times 0.5 times 0.5, 50.8, and that could give us a range of, say, reasonable numbers that we could expect here, 469 all the way through 531. Okay, anyhow, so this is why we do not need any standard deviation statement here. Okay. A couple of things that are slightly more complicated. Yeah.
Does that only work for dummy variables?
Yeah, for proportions. Yeah, so where we have a dummy question, so to speak, a yes or no answer that will give us a proportion of yes sayers, so to speak, and then we have this for binomial self. Otherwise, you don't have it.
What is the n in our example, our input right now?
Well, the n we're trying to figure out. N is the sample size. Right, so the n here was 1,000 tosses of the coin. That answer it already, or looks like it doesn't help?
Yeah, if n is our sample size, like the thing we're trying to find, what is that 4, 60, 95, 31?
This would be a confidence interval, 95% confidence interval, for the number of times that I throw heads with a coin, if I throw 1,000 times. Okay, so let's see. We had this, and that led to that. Obviously, if we're trying to compare not 30 versus 40%, but 60 versus 70, we get exactly the same thing, which is should be totally obvious, because the only difference between this one and that one would be recoding all the ones to zeros and all the zeros to ones. That doesn't change a bit to the whole problem itself. So it's not so weird that both this one and that one lead to exactly the same number over there. Okay, just a recoding difference. However, here it starts to be different. You might be tempted to think that this difference of 1 is actually completely defining the whole thing, just like the difference between 115 and 120 was for the t-test. Here is different. Here you see, for this difference over there, 0.1 to 0.2, which is also a 0.1 difference, you see that sample size, the necessary sample size, decreases actually. So when we are with something where we are comparing stuff near the edges of 0, 1, so either close to 0 or close to 1, then our sample size can be smaller. Here, this is actually where, this is the worst place to be, so to speak. If you want to compare 0.45 to 0.55, again, a 0.1 difference, but now around 0.5. Now this is the worst place, 1,048. And one way to get that is if you go back to this one. Here you see that standard deviation that determines how wide the confidence interval is. You see that this, if you maximize this is maximum, p equal to 0.5 as a maximum right in the middle. So the standard deviation is widest. You get the widest confidence intervals when we are near 0.5, and it gets better as we get near the edges. So it's easy to mix up. In the t-test there, 115 versus 120, versus 105 versus 100, or 50 versus 55, none of that matters. For the proportions, it does, and quite a bit. Okay, so what you need to know about this, you need to know first of all, the commands, of course. So you have to know how they work and which number to look at, and that this is really 524 per group, and that the total n then would be 1,048. And besides that, you need to know the different options that the commands have. You saw already a couple, and there are actually a couple more, and understand in which direction the sample size changes dependent on these parameters. So, bigger difference, okay, sample size will go down. Smaller difference, sample size will go up. Standard deviation, bigger, sample size will go up. These kind of things you have to know by heart as well. Okay, this one I want to skip for now. I talked about it already, so let me just burn it in. Two-sided tests and one-sided tests. The number one rule to remember, okay, let's stick to two-sided tests because that's the safest. One-sided tests assume that you have a clear idea in which direction the alternative hypothesis is going to go. So I suspect my coin is showing heads way too often, and I want to check if it really is any different from 0.5. And the only reasonable alternative that I have is that it is larger than 0.5. That would in principle be an argument to use a one-sided test. But the standard counter-argument to actually using this would be, well, if you depend on that argument to find an actual difference, then you have to be really, really sure that you thought about this argument up front and not afterwards. Okay, if you say, okay, let's put all the probability mass, all the 5% on one side, and then my hypothesis is rejected as I wanted, then, yeah, you might be susceptible to other people thinking that you are committing fraud. Let's see how this goes. Let's see. Yeah, this is the one t-test example where, in fact, you see an example where Stata gives different kinds of tests, one-sided in one direction, one-sided in the other direction, and this is two-sided. So there I said simply focus on the one in the middle. That's the only one to look at. Another one here too, Fisher's exact, will give you a one-sided Fisher's exact. Do note that the number there typically goes down. So if you want to find a significant difference, it's easier to look at one side because these numbers get below 0.05 faster. So that would, in principle, help you, but whenever Stata gives it, by default it will be two-sided, and the suggestion is to stick to two-sided. You can ask for one-sided test if you really insist, and then you will see indeed smaller, there, one-sided will deliver a smaller sample size. So one-sided is, let's say, good for you, and because it's by definition good for you, we typically don't do it, and we stick to two-sided. Okay, one final thing to try to grasp, and let's say mess with your mind at least a little bit. That is what's called a stratified sample. All of this up to now was about you have a big population somewhere, and we're sampling from that at random. Now, one question could be, especially given that we get such large numbers, couldn't we do any better than that? And there is a way to do better. If you can stratify your sample in different kinds of groups. So let's suppose that we have, let's say for ease of exposition, two groups, males and females, just as an example. But you could, in principle, generalize this to way more groups than that. Then, if you go through the math that belongs to this, we're not going to do anything in Stata with these kind of things. It is good if you at least remember how this works, because as soon as you need to actually collect data yourself, this one can save you a lot of time and energy. If you can divide your sample in, let's say, two groups, then you will see, if you do the math or follow the math from somebody else, that the actual sample size necessary from that particular group depends on two things. On the size of that group. This is where it starts to get weird, because the population size at first didn't matter, but for stratified sampling it does. The size of that group and the variance in that group. Okay, the variance is easy to understand. If I have a group here, males, for instance, and they do not vary a lot. I want to ask them a question and there is no variance or hardly any variance in their answer. Then I would be, why would I ask 1,000 males if I get no variance? They're all saying 3. If I know that the variance is small, it would be weird to put half of my sample in the male group. Okay, so the variance is low, and I want to have as low samples as I can get away with. If I have something that is really wide in terms of variance, everybody says something else, then to measure that appropriately, I need to have a large sample. Okay, so that's the thing to go by. If you look at different kinds of groups, where I have K, and you have an estimate first of the size of that group in the population, here labeled NK, and an estimate of the variance on whatever it is that you want to measure of that group in the population. And you take the product of the two, and that itself is your measure for how large of the sample should be in that particular group. So if I have only two groups here, one group, let's say, is equally big as the other one, 10,000 goes one, and 10,000 goes something else. That doesn't help much. You have n variance. Variance here is 2. Variance here is 20. I know that in the end, let's say I have money for 100 or 1,000 samples. What do? I look at these. 2 times 10,000 is 20,000. 20 times 10,000, 200,000. And that is the distribution that I use for my sample. So I choose cases proportional to that number, to that product we have over there. And that will certainly help a lot in trying to get the sample size in the end down or the precision up, whatever it is that prefer. But of course, what you need for this is that you have a group for which you know the variance in there is not very high. If you don't know it, then yeah, there's nothing you can do. Yeah.
So is it that you, is it in practice that you calculate for the right case in that example, then you calculate the sample size and then you just say, okay, for the other group, I need this proportion less to get sample size? Or is it
Yeah, so if I would say, this is 10 times as large as that, so here I take 100, here I take 10, for 110 in total. And that would be smarter than if I have 110 in total, dividing them 55, 55. Because there on the left, they vary way less. So I shouldn't put so many measurements in that group.
which a reference sample is of the right group, with the most variance?
What do you mean with reference sample?
So you have to take one amount of, yes, one sample as a reference to divide by 10 or to multiply by 10.
Yeah, all this says nothing about the total sample size. It only says something about the distribution of sample size across the different groups that you have. And we're not going to bother with this in Stata's power command. But if you ever have to collect data, then this can save you, massive. Any questions left? Yes.
Do I have to be able to do all this in Stata?
What do you mean by all this?
All the commands you showed, should we be able to type them up?
Yeah, not the Stata do file with the simulations, but all the other, the power 2 means and the power 2